Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video, this final theory video for this chapter, we're going to go over epoxides. Okay, so epoxides are three-membered rings that include oxygen, and there's a few things that we need to learn about them, how to name them, or at least be familiar with the naming of them. It's not as popular in exam, but you should know how to name them. Also learn about their synthesis and reactivity. So let's get started. So the first thing I want to talk about is the nomenclature, and there's a few different ways that you can name them. The first one, A, is if we call it as a substituent known as an epoxy group. So, by the way, an epoxide in its general form is right here. This is called an epoxide, and this is also known as an ethylene oxide. It's the simplest epoxide that you can have. Okay, so a three-membered ring with O is an epoxide. Now, epoxy as a substituent is, for example, let's say I have a cyclohexane and there's an epoxide on it. So one way to name this is to say that we have a 1, 2 epoxy cyclohexane. Okay, so that's how we would name it. We say the position of the epoxide, 1, 2 in this case, and then we use the word epoxy. So another example, let's say we have something that looks like this and there's an epoxide here. Well, we can name this as if it was an alkane, right? So we could say that this is 1 and 2, 3, 4, and 5. So all I'm doing is trying to get the O on the lowest possible number, right? So this is a 2, 3 epoxy, and then in this case pentane. See that? So we just name it, and we actually do cite both positions 2 and 3 because sometimes the oxygen extends beyond and it's a very similar nomenclature. So we do say where the two positions are, even though in our case they're going to be right next door neighbors. Now this could be also like, let's say, a cis. So if this is a wedge methyl and this is a wedge methyl or wedge ethyl, then this could be called a cis 2, 3. Whereas maybe I have an epoxide and this is wedge and this is back, right? So this would be a trans. So epoxides, because they're in a ring, if you have the groups on opposite side, it's trans. On the same side, wedge or dash, it's cis. Okay? So that's another, this is a way to name it as what's called an epoxy group. So this is as if it was a substituent. Now, another way to name epoxides is these oxyranes. So you can call it an oxyrane. Now that means that that's the parent. This is the parent now. So as a parent, it's called an oxyrane. So for example, let's say we have over here an oxygen, and then let's put 2 methyls right there. So we could call this a dimethyl oxyrane, but we wouldn't know where those methyls are. Are the methyls on the same carbon or are they on opposite carbons, right? So that we have to have a better way to name it, and this is how we do it. We number 1 for the oxygen and then 2, 3. So it's 1, 2, 3. And so what we're going to say is we have here a 2, 2 dimethyl oxyrane. And the idea is, remember, this is the simplest oxyrane right here. This right here is known as also an oxyrane. Actually, I'll draw it down below. So an oxyrane looks like that. Oxyrane. And so in our case, we're having branches off number 2 of the oxyrane. Now, clearly, we're going to use this nomenclature if we can name the branches. If it's too complicated, then we would go up and call it an epoxy group, right? Okay, so in this case, we have a 2, 3 dimethyl oxyrane. I'm just going to wrap around to the next line for space purposes, but it's really one continuous word. Okay, and that's how we name oxyranes. So again, if you have something that's like, for example, let's say we have an epoxide and there's an ethyl side and a methyl side, then we would number this based on alphabetical priority, right? So this would be 1 and ethyl before methyl for 2 and 3. So 2 ethyl dash 3 methyl oxyrane. So you see how you use that? So as long as the branching is simple, then we call it from its three-membered ring as an oxyrane. And that's it. That's how this works. These are a few different ways of naming the epoxide. There's the epoxy as a substituent, and then the oxyrane if it's the parent, and that's basically how this works. Okay, now let's do epoxide synthesis. So for epoxide synthesis, there are two ways that we can do this. The first one is actually something we know from a while back with alkenes. It's called the Hallow Hydron reaction, and we follow up with an SN2, intramolecular, intra. I'll write intra. Now, for example, let's say I have a system like this, and I treat it with Br2 in water. Okay? Now, what you have to remember is a few key points. This is an anti-addition, right? The Br adds anti with the OH, and we also have to remember that the OH is on the higher degree. These are things that we talked about because we make a triangle bromonium ion, and then the O comes in second, but we're not going to do the mechanism. We're just going to go right to the answer. So if this is tertiary and this is secondary, we wind up getting a Br over here and an OH over here. Now, let's say for argument's sake that this Br is on the wedge. Then that means O is in the back, right? Because it has to be anti. And then, of course, if there's a methyl, by default, the methyl must be on the wedge, right? Because that's the only bond left. Each bond in the ring has a wedge and a dash, and so that's how we came up with this. Now, what's interesting about this is that once you add it together this way, notice that the OH is exact backside of the Br. So if I was to use a base, I'll write A minus, but it doesn't matter. It could be, for example, NaH or NaNH2 or OH, NaOH, or lithium with an R group. It doesn't really matter what the base is, but a base will pull off the H and make that oxygen negative. Once the oxygen is negative, and I'll just put the wedge here to put it out of the way, and here's a wedge Br. Once it's negative, now the oxygen can fold in through an SN2 attack. So through SN2, we can have this O come in and the Br leave, and that gives us the epoxide. So I want to make it clear that it's not just in the back, the O. We could have had the O come in from the wedge, right? If the Br came in from the back, then the O comes in from the wedge. So it's that plus an enantiomer, right? So you don't just have one answer. You'll get both. You'll have that, plus you'll have the O that came in from the wedge. And that's because the Br came in from the back. So you do get both answers as possibilities. So that's, not really the critical part here. So what's important to note is that you can do a halohydrin and then throw in some base, and the O swings around and throws out the halogen. And of course it could be Br2, Cl2, I2, F2. It doesn't matter what the halogen is. It's just going to go through this. And typically you want Br or I because they're better leaving groups, right, than Cl or F. But that's pretty much how it works. So generally Br2 or I2 would be the best, but don't get caught up on that. Any halogen will do here to do this job. Okay, so I won't even write that down because it doesn't really matter. All right, that's one way. And now another way to do this, B, is to do what's called using a peroxy acid. So a peroxy acid allows us to actually make an epoxide in a concerted fashion. Concerted, or remember how concerted always means Syn addition. So the O winds up Syn at the end of this reaction I just showed you, right? Because the O is in the back or O is on the wedge, but it started with an anti-type reaction. Whereas what I'm going to show you now is a Syn addition. So imagine if we take, let's say, the same alkene, and I treat it with R, C, double bond O, 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 and H. So this is a peroxy acid, right? We have a peroxy group right there, two O's connected, and then there's an acid like a carboxylic acid. So what winds up happening is the O on this end winds up attaching onto the carbon while the double bond attaches onto the O. So there's kind of like this exchange. And what we wind up doing is we get oxygen to take right into the center of this alkene. So we wind up getting the oxygen to cover both carbons at the same time. So this is a concerted process where the O transfers over at the same time. Now, we also wind up making a carboxylic acid from this, but that's not as important to really realize. What's happening here is very simple. This becomes a carbonyl, and this double bond O opens up and pulls that H over there. It's not really important to worry too much about that.